All right. Hello, grade 10s. We're into the next unit. We're going to start on chapter 10 and section 1 here. That's where we're going to start. And it's about optics, the study of light and devices that use light. So before we do this, we better figure out what light is. So light is a form of energy. And it's radiant energy. The word radiant comes from it radiates, it spreads out in all directions from some source, like a light bulb. The light bulb doesn't just shine one half of the room. Light bulb usually shines up the entire room, moves out everywhere. Now, this thing called light that we're going to study, as you know, sometimes it's natural light, might come from the sun, might be artificial light, come from a light bulb. And unlike other types of radiant energy, light is very special to us because we can detect it with our eye. That's why one of the main reasons we're going to study it. It's a big part of our life, this thing called light. Now, there are other types of radiant energies that are related to light, like radio waves, way down here, different type of radiant energy. Microwaves, you use it to maybe heat up your popcorn. It's also used for telecommunications off cell towers. Infrared waves. We can't see them, but if you put your hand out under an infrared light source, it'll heat up. Maybe you've been to McDonald's or Burger King or someplace and you see these light bulbs keeping French fries warm as they're being waited, as they're waiting to be served there. All right, that's infrared heat. Ultraviolet rays, I've circled them. UV, you probably heard of them. Got to be careful. The sun puts that out, puts all of these out actually, and but the UV waves they can cause sunburns and then like get enough of them and it can increase your chances of skin cancer. It's a type of radiant energy, but our eyes can't see it. X-rays. You go to the dentist or the doctor. Gamma waves, gamma rays, very dangerous, highly radioactive if you're exposed to them. So these are all forms of radiant energy, but our eyes only see this bit right here, visible light. That's the only part that we see. Now all of these together, from radio waves all the way through, they make up what these radiant energies together, they make up what's called the electromagnetic spectrum, and that's going to be a big part of what we're studying uh, today. Now, there are a lot of different kinds of energies that travel in a phenomenon called waves. Light is just one of them. Sound waves travel. That's how we speak to each other. It's not a light wave, it's a sound wave. You might be able to vibrate a spring or a string or a skipping rope when you were a kid. It's a wave traveling through a material. And sometimes the waves look all bunched up together where their peaks called crests are really close to each other. And that distance is called a wavelength. So this would be a short wavelength. Sometimes the waves are not bunched up together. They're spread apart from peak to peak. Crest to crest is longer. That's a long wavelength. Let's take a look at some waves. It'll be fun. So here we are. This is something that's going to vibrate in a moment and it's going to create a wave. Watch. There you have it, back and forth, and it's creating a wave. Now this wave is caused by the vibration here, but there's not many vibrations per second. Not many at all. It doesn't happen very frequently. So what a scientist or a physicist would say is this has a low frequency. It doesn't happen a lot. And so the wave itself has a low frequency. Take a look at this green part of the material. Let's pretend it's a spring that this energy is moving for. Look, it doesn't move up and down that frequently as the wave goes through it, right? The wave's going from left to right. the material stays there. It's the wave that goes through. But I can change that by changing the frequency. Remember I said, hey, it's not vibrating back and forth very frequently. Well, let's increase the frequency. Let's really increase it. Let's see what happens. Yeah. Now it vibrates back and forth more frequently, and the wave has changed. And every particle here, look at this green particle right here, right there, boom, 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 very frequently going up and down as the wave energy goes from left to right. The other thing that you may have noticed is that the peaks, the distance from peak to peak, which is called the wave length, the length of the wave is quite short. Look, I can actually measure it. Looks like it's, yeah, 2.1-ish centimeters, right? So we can change not only the frequency, but the wavelength as we change the frequency. Let's run that through again, and let's not have 3 seconds of vibrations, or 3 hertz of vibrations, 3 vibrations per second. Let's go to 1.5, or 1, that's 1.62, that's fine. All right. 1.62 vibrations per second, or 1.62 hertz. Let's pause it. Look what's happened. The wave is not as bunched up as it used to be. The distance from peak to peak, or crest to crest, known as the wavelength, is longer now. There you have it. Okay, so that's a very important property of waves. And the other thing we can change is the amplitude, how big the wave is. So let me move this ruler out of the way, and let's set up a, there we go. So the amplitude is how tall is the crest. So it's like 0.2, 0.4, it's about 0.6. Or it has to be the same for the underneath, the reverse crest. It's called a trough, to be technical. That is called amplitude. How big is the wave? And I can change that as well. Watch. Now the frequency remained the same, right? But how long the vibration is changing from this middle point, this rest point is changed. So this is a big amplitude. So these are some of the neat characteristics of waves, and there's many types of waves, water waves, sound waves, but we're going to focus in on light waves. So here we are from our little detour with that animation, and I put the link to that simulation on today's news, today's announcement. I beg your pardon. If you want to play around with it, there's a link to it. So let's continue with our note. So some energy waves need a medium. That's a technical word for a material. They need something to travel through, like air, water, or a spring, like in the animation we had, through which to travel. The medium moves back and forth as the wave travels through it, but does not actually travel along the wave. You probably, or I hope you remember, I was showing you the green dot every once in a while. I was moving up and down. It wasn't moving left to right with the wave. It's the wave that moved left to right, not the particle itself. Now, light is very interesting because it can travel through a vacuum, through emptiness where there's nothing. If this wasn't true, sunlight would never reach us. So how does that happen? What's vibrating if there's nothing there, if there's no air or water or a spring to vibrate? What's vibrating? Well, let me give you a brief look at that. Light is a combination of electric and magnetic fields moving together through space. It is electromagnetic radiation. Now, maybe in grade 9, your teacher maybe got an ebonite rod, a plastic rod, or plastic ruler and rubbed it with some fur and then put that rod close to the water, and all of a sudden the water bent. That's because there was a presence of an electric field. Maybe you played with magnets. Magnets attract each other, they repel each other. Why? There's a magnetic field there. And here you can see a magnet with some pieces of iron all lining up with a magnetic field. You may have seen a picture like that in the past. How are these things related into light? Well, in light, It's a vibration of a combination of electric and magnetic fields that move through emptiness. Now, that's all I'm going to really say about this because this really moves into the area of physics. If you really want to get into this more deeply, you would take a physics course, and I teach them at Wesleyan for the time being. And these are some of the areas we would investigate. So that's really good. All you really need to know is the thing that's vibrating is electric fields and magnetic fields together, and it's called electromagnetic radiation, and that's what light is. So one amazing feature of light is that it does not need a medium or material to travel through. In fact, it travels most quickly in emptiness, and the technical word for emptiness is a vacuum. Now, light is the fastest thing in the universe. It travels at 300 million meters per second. There it is, 300 million meters per second. But most scientists use scientific notation to write that. 3.0 times 10 to the 8 meters per second. All right, and we can convert it into kilometers as well. So a little bit of a recap here. A wavelength is the distance between two adjacent crests or troughs, right? There's a wavelength, crest to crest, or trough to trough. We saw that in the animation. The amplitude is the height of the peak or trough. The greater the amplitude, the greater amount of energy transferred. So here's an amplitude from top of the crest to what we call the rest or zero position. But I could also measure it from the bottom of a trough to that zero or rest position. It doesn't matter where you measure it. The frequency is the number of cycles or wavelengths in a given period of time. The wave on the right has a shorter wavelength and therefore a greater frequency than the one on the left. Yep, right here. Big wavelength, very low frequency. Short wavelength, really high frequency. And we saw that in the animation as I was changing frequency, the wavelength changed along with it. So let's bring this all together. Light and the electromagnetic spectrum. The electromagnetic spectrum. Light is a form of energy. Visible light is only a little bit of that type of energy that surround us every day, but it's the part that we can see. We are also surrounded by invisible light-like waves, which together with visible light are called the electromagnetic radiation. Electromagnetic radiation is a wave pattern made of electric and magnetic fields that can travel through empty space. So we're just recapping what I said earlier. The entire range of electromagnetic radiation extends from the shortest gamma rays to the longest radio waves and includes light. This range is called the electromagnetic spectrum. Let's take a look at it. Here it is. Visible light is just this little bit in here where things vibrate from 7 times 10 to the 4 hertz for blue light, very high frequency, to red light, 4 times 10 to the 14 hertz, lower frequency. Red light has a lower frequency and a longer wavelength. Blue light has a higher frequency and a shorter wavelength. And you can see as you get shorter and shorter wavelengths, you get into things like ultraviolet light, X-rays, and gamma rays. The further you go this way, the shorter the wavelength, the higher the frequency, and the greater the energy. This can cause cancer. X-rays are so powerful they go through your body. Too much ultraviolet light will burn your skin. So a lot of energy here. Then with longer wavelengths, right, and lower frequencies, you get into infrared, which we experience as heat, and then microwaves and radio and TV waves down here. So here's been our introduction to light, our new unit. Please watch the other video. The link is there. I got a link to another video. Please watch it. It's actually quite well done. And we've got the simulation link. I've posted some notes. And also, we have a request for you to read section 10.1 in your textbook. So I hope you have a great day, and we'll be back tomorrow. Bye-bye.